This video will cover the material for section 5.1 of our course textbook. In this video, we're going to be simplifying radical expressions and evaluating radical functions. Let's start with the definition of the square root. For example, it states, square root b is the square root of b squared equals a. All right, so b represents a number that multiplied times itself will give you a. Something to note, a square root cancels a square and squaring cancels a square root. I will give you examples of what all these words means. All right. Other definitions of positive and negative square roots. The square root of a is a positive square root of a. All right. The answer will be positive. If you have a negative in the outside, once you take the square root, the answer will be negative. The square root of 0 will always be 0. And the square root of a negative number is not a real number. And we'll learn that towards later in the course. All right. Let's see a few examples about what this all means. So if we have the square root of 36, one number multiplied times itself will give you 36. That will be 6. Okay. And then again, one number multiplied times itself gives you 36. Here you can rewrite it if you would have liked. 36, square root of 36 over square root of 49. You don't need to do this step, but that will be 6 over 7. Then here, what will be the square root of this decimal? All right. The square root of 0.04 will be 0.2 because 0.2 times 0.2 gives you 0.04. As stated above, any negatives inside the square root is not a real number. All right. However, here inside the square root is a positive, so that's going to be positive 12. However, when it comes out, it's a negative. That negative is waiting for the 12. Okay. Then as well, here we have the same scenario. Square root of 1 is 1. Square root of 9 is 3. But we have that negative waiting for us in the outside. All right. Let's see more examples. Now, sometimes we're going to be simplifying radicals that are more other than just the square root. We can have the cube root, the fourth root, the fifth root, and so on. When you think about the square root, think about groups of 2, and cube root groups of 3, fourth root groups of 4, fifth root groups of 5. Okay, let's see a few examples here. So one number multiplied times itself gives you 4. That will be 2. One number multiplied times itself 3 times gives you 64. That will be 4. One number and multiplied times itself 5 times will give you negative 32. That will be negative 2. One number multiplied times itself will give you negative 36. That will be not a real number because it's negative inside the square root and it's a square root. Then we go to number 11. One number multiplied times itself 3 times will give you 1000. That will be 10. And then one number multiplied times itself 3 times will give you negative 27. That will be negative 3. And this is because negative 3 times negative 3 times negative 3. The first two negative gives you a positive 9. And then times the last one gives you negative 27. All right. Now, something that is good to know is that when whatever the index, which is this right here, is raised to the same power, the exponent in here, you can literally just cancel out the exponents, and that's going to give you a. All right, and it will be the absolute value of a. Okay, so for number 13, this is to the fourth root, here's to the fourth root. Whatever is inside here. Now, this is the exponent here. It's a 4, a positive 4, which is an even exponent, all right? Notice how it says here, even, okay? This is going to be positive 3. However, when it's odd, all right, the a will stay as it is. In this case, whatever is negative or positive. So here we have this cancels. These are odd exponents, so that will be negative 3. Right here you don't see, but that's a little 2. So these 2 cancel, and that's an x plus 2. All right? Now, there will be times where whatever is inside the square root or cube root, whatever is inside the radical is not perfect. And we need to simplify that. All right? Always keep in mind of grouping based on the index. Okay? So we have this example here, y to the 8th. Well, 8 is not a perfect, well, let's think about 8 is not a perfect square. Here I was going to confuse myself. 8 is not a perfect square, but what are we dealing with? Exponents. Yes, yes, yes. Exponents. I cannot write. We are dealing with exponents. So we treat them differently. We are simply dividing by the index. With exponents, we divide by the index. Let's keep that in mind. What is the index here? At 2. We don't see it, but we know it's there. So 8 divided by 2 is y, 4. That is only for the exponents, all right? Okay, next example. What is the cube root of 27? That will be 3. And then we take the exponent and divide by the index. So that will be a. All right, let's just make sure we keep that in mind. It's super important. All right, super important. Exponent, I cannot do a star. Oh, cannot do a star. Well, you know what I mean, right? Yes, you do. I know you do. All right, so cube root of 64, if I'm not mistaken, that is a 4. And then we're going to take the 12 divided by the 3, which is the index, and that's going to be y, 4. One number multiplied times itself 4 times gives you 81. Let's see if 81 is a perfect fourth. I think it's 3. 3 times 3 times 3 times 3, 81. Perfecto. Then x divided by 4 is just 1x. Y to the 8. So 8 divided by 4 is just y2. In the denominator, one number multiplied times itself 4 times gives you 16. I believe that is 2. This negative is here. It's waiting in the outside for us. So we just have to bring that down. Or let's say better, bring it over. Okay. I have not been boxing my answers. Okay. Moving on. So again, please keep in mind, we treat the variables different. All right. The exponents are being divided by the index versus the numbers. You're asking yourself, one number multiplied times itself this many times will give me this number. All right. So I'm have 8 divided by 5. 5 divided by a is just a. And b divided by the 5 divided by the 5 is just b. Okay. Here the square root of 4 is 2. Now can you divide 3 into 2? It will not give you a whole number, but you can ask yourself, how many times does 2 fit into 3? That is 1 time, and 1 left inside. How many times thus 2 fits into 5. That is 2 times, and you have 1 left. So when you have this one, you need to simplify it because it doesn't always work out nicely like the previous one. So think about it like division. For the exponents, have division in mind. All right. One more example right here. So square root of 25, well, we know that's 5, right? Then remember the index is a 2 here. How many times 2 fits into 7? That's 3 times, right? And 1 remaining. How many times 2 fits into 6? That's, I'm gonna go ahead and write it. That's 2 times. And non-remainder. Yeah, I hope you saw that I wrote that wrong, right? B3. All right. Then how many times 2 fits into 3? Only once. And 1 remainder. So when we rewrite this, we have 5a cubed b3c ac. I think what could be the most complicated part of this is the fact that you have to remember to treat the exponents different than how would you treat the numbers. All right. Now, one application when it comes to radicals that we can use is using the Pythagorean theorem to solve scenarios like the one we have here. Now, the Pythagorean theorem is a squared plus b squared equals c squared. All right. Let's read different scenario. Take a moment to read it. All right. So it says you are locked out of your house and the only open window is on the second floor, 32 feet above the ground. All right. You borrow a ladder from one of your neighbors. To lay along the window, you notice that there's a bush along the edge of the house. So you'll have to place a ladder 15 feet from the house. What length of the ladder do you need to reach the window? I'm going to attempt to draw a house like I have been doing since I was in kindergarten. Maybe I can try to make it a bigger house, you know. Usually do the small traditional ones. All right. I'm going to pretend like this is the door. Wow, that is a fancy house right there. Anyways, you notice that this is a window right here. All right. And there's a bush right here. Ooh, bush. So you have to take your fancy little ladder. Ladders are usually silver, but this time we'll use blue. You have to place it here, right? At this angle. Okay. So the problem says the height is 32 feet above the ground. So this length right here is 32 feet. All right. And then it says that the ladder, you're going to place it 15 feet. If you go based on what a right triangle looks like, oh, that is not a nice triangle. Let's try it again. Oh, it just took me all the way to the top. Okay. If we think about what a right triangle looks like, we have A, B, C. Try to match that to your little picture here. This is 32, 15, I don't know. And using this information where the Pythagorean theorem comes from, we can find the length of the ladder right here. So we are going to have 32 square plus 15 square equals b squared. So then I'm using my calculator. 32 times 32 gives me 1024 plus 15 times 15, 225. I go ahead and add that. Gives me 1249. Did I add that right? Yeah. B squared. Remember what we said about in order to cancel a square, the opposite is to square root it. That's what we're going to do here. Go ahead and square root that. That gives you 35.341 and a few other decimals. So rounding it to 35.34. Right? And that will be the length of the ladder. We have one more example, very similar to evaluating rational functions and evaluating quadratics and evaluating linear functions. It's basically we're giving you an x value and you're going to substitute that into the function to find the y value. So when f of x, oops, let's try that again. F of 0, I'm going to substitute that 0 for the x. Then I have f of -1. Substitute that -1 for the x. And then I have f of 3. Substituting that 3 for the x. So at the first one at the top, we have 2 times 0 is 0 minus 5. That gives you not a real number, right? Because it's -5. So this one is not in the domain, not a real number. So this one is no good, right? Here we have 2 times -1. So that's -2 minus -5. That gives you -7. And again, not a real number. I did not pick good numbers here. But at least we can see. And here we have 2 times 3, which is 6, minus 5. Oh, yay! One that work. Amazing. So square root of 1 gives you 1. So when x is 3, y is 1. However, for the first two, not on the domain, not a real number. All right. So those were examples going over section 5.1 of this course textbook.